Okay, so how many of you know machine learning? What is it about? Because I made some small introduction. Okay, it's good I cut it down even further. So maybe someone heard from the introduction that I did optimization. Actually, I did FMA program here, which is financial math. But now I somehow do AI. And the question is basically why I do AI. Because my PhD was optimization. So basically, how did I try to get into this applied AI and not optimization? So basically, when I was in States, I find out that there are so many bridges which are falling down. There are earthquakes, there are floodings, and so on. And I was asking my colleague from the civil engineering department that how often do people check bridges, right? Do you know how it is done to check bridge, if the bridge is okay or not? Do you want to guess?
Visual inspection?
Visual inspection, how often?
Once in 10 years?
Once in 2 years. In USA, once in 2 years. The biggest bridges, they go once in 2 years. They put some sensors. They put one car to go up and down. They measure something. They say it's okay or it's not. So some thought, hey, why don't we create some kind of AI system which can always monitor the bridge? There's earthquake, we can see now it's broken, maybe try to do inspection sooner, and so on and so on. So basically now we already have some prototypes running on some bridges in States, basically always monitoring the bridges, trying to tell you it's okay or there was some structural change, maybe try to check it out, okay? Cool. So how does machine learning work? You told me many of you know, and I was asking my daughter that how does it work, machine learning? And she told me that is very easy. You take the machine, you take a lot of books, right? Ask the machine to read the books, understand the books, right? Afterwards, the machine will graduate and then go to work and work for the end of their lives, right? Is she correct? What do you think? Is she correct? When I was asking this question, people asked me, why do you force her to study the chemistry, right? She likes it, doesn't matter. But is she correct or not? What do you think?
Depends on the book.
Depends on the books, okay. But in general, we take any books we want, we feed to the machine and so on. Is she correct or not really?
Well, not today. Not today.
Okay.
Because I mean, typically the machines are created out of already ones that are studied for a while.
Okay, so I like your answer. She is wrong. Try to tell her this one, but she is wrong because there should be some loop as well, right? Usually we create some machine program, we then someone try to feed new data, we try to correct AI and so on. So there should be some loop as well, which she missed. Okay, so I will speak about optimization because I did FMA here. So let's get some start with like my journey as a student here, right? With the optimization, the first class, we learn about simplest method maybe. How many of you know about this simplest method? Maybe some of you know, right? And then we learn many problems, let's say transportation problems, some of them, or some assignment, or maybe some kind of like a mixture of things to find out the right balance. And basically we understand, yes, we can solve them efficiently. There are many algorithms how to solve linear programs, right? Then later on, we learn this, let's say, vehicle routing problem. Do you know this vehicle routing problem? You have some depot, you have a bunch of customers, and the car has some capacity, right? And every customer wants to have a few items of some goods, and basically your ask or your task is basically to try to assign the routes which will minimize the cumulative distance, for example, right? Such that every customer has to be happy. He will get the items he wants, but also there's a limit on the capacity of the vehicle, right? Basically, there's no capacity on the vehicle. The shortest path is basically traveling certain problem, right? Maybe you heard about this one before. Okay, if you want to solve this one exactly and find optimal solution, you will need some binary variables to formulate this as a problem, right? The problem is that now you can solve maybe instances up to maybe 60 customers to optimality. So it's actually very hard, right? And actually one of the approaches is called branch and bound. I don't want to go into details, but there are many softwares which you can use to solve these problems for you, okay? So people are usually happy, you can solve them maybe exactly if there's small instance, but this is an exponentially hard problem, this one. Okay, if you try to go and formulate this one as an optimization problem, basically you want to minimize some kind of distance with this xijk is equals to 0 if the vehicle k doesn't go from customer I to customer j, is equals to 1 if you go from I to j for the vehicle k, okay? It's very simple formulation. And basically the dij is basically the cost of getting from I to j, okay? So basically if this equals to 1, I have some cost, otherwise I'm happy. And there's a bunch of constraints. Some of them tells you can go from I to I. The last one tells you that every node you enter, you also have to exit, and so on. And you also have some capacity constraint for each vehicle that you shouldn't exceed much more than the capacity of the car, okay? You put all these constraints, and then you find solution like this one. Is this okay or not? What do you think? Is this a valid route for the car to go from depot to customers? Is it valid or not? Clearly not. Why? Come on, guys. It's disconnected, right? So you need to have additional constraints, which is, for example, this one, to put additional constraint that for every cut, basically, which just include basically some depot, you need to also enter and exit, right? So basically, if someone use this cut here, so I don't have any connection from this cut to the rest, okay? So clearly, this is not, without this constraint, basically, I can produce this one. With this constraint, it will be actually a valid solution, okay? But there are two things which are here, this dij and qj. What are those things? Dij is the cost from I to j, right? Is this given or is this not given? What do you think? If I ask you, I want to go from, let's say, Bratislava to Košice, right? What is the cost? What's the distance? Distance, we know distance, right? If I say, I don't care about distance in kilometers, I care distance in hours, right? Do you know distance? Or to Prague? Do you know, can you tell me the distance from Bratislava now to Prague in hours? It's not really given, right? It's random, right? So basically, actually, knowing these quantities, it's very hard to know for sure this is the distance because you can have some accident, you can have some additional work on the streets. Actually, it will be very complicated. The same, sometimes even the demand can be quite complicated to know exactly what is it. Sometimes we have just distribution, right? So basically, in the other research, basically someone said, like, how can we solve this VRP when the distances or the cost from getting I to j can be random? And also, basically, we can also have different constraints. Maybe also the customer demand can be random, okay? So usually in the world, many things are stochastic and some driven by external features. For example, in this case, you can see the travel time from some city to different city can be clearly affected and correlated by weather, right? In Bratislava, when you get the snow, getting here from maybe Mlinské Nivy can be like 2 hours, who knows, right? Because there could be some like traffic issues, right? So clearly, if you have some snow in some location, all those neighboring distances will be also affected, right? The same demand for different items can be driven by some external features, like temperature outside, right? Imagine I have a shop which sells ice cream. I don't know my demand, but clearly demand will depend on the weather outside, right? There is 50 degrees outside, you will sell more ice cream. There is -10, you will sell less ice cream, right? So clearly, if I have this optimization problem, which can be VRP, for example, I have some elements going to the model, and they are usually stochastic, right? And some driven by some external features, maybe temperature, rainfall, and so on, okay? So this was our task. How can I use something to solve this stochastic VRP, okay? So what is the traditional approach, what people somehow did in the past? I take some data which I have from the past. Maybe I know the temperatures, I know the rainfalls and so on, I know the customer demands, I know the travel times from the past. What I can somehow do, I can just build some model, right? I can feed the data, maybe I will do regression, doesn't matter what I do. I will input some features, I will have some real value from the past as the targets, I will fit some distribution, some model, right? Maybe I try to maybe assume that my random variables will be random, okay, Gaussian, right? With some unknown mu and sigma. So basically I can build this model to tell me, given the features, the distribution will be random with this mean and this variance, right? Does that make sense? Also, I can maybe also assume that my correlations will be basically 0, right? Because it's very hard to estimate. So basically, usually what we do, we assume the data will be, these random variables will be random, Gaussian, independent from each other, with some means and variances, right? Then build a model. What I do afterwards? I can observe the features now or for tomorrow. I can go to the model, estimate the mu's and sigmas. Then I will sample a few scenarios. Then I can formulate this mixed integer program with those scenarios in mind. Afterwards, I can use the solvers to find some solution, and then I'm happy, right? In some sense. So what are the issues here? What do you think? What are the issues with this approach? Does it make sense so far? Guys, does it make sense so far? I want to solve some routing problem, which is stochastic, right? I have some data from the past. I can assume something about the randomness, right? Maybe I will assume they're independent, maybe they're Gaussians. I just need to estimate the mu and sigma, right? If I know the mu and sigma, I can just sample a few randomizations, right? I can basically maybe go here to this huge model and somehow replace these DIJs by some scenarios, right? And some try to minimize the expectation or the average over some scenarios and find the routes, right? So what is the issue with these models, or with this approach? What do you think?
I mean, I have a few issues.
I also have a few issues, yes.
So one is, for example, there can be correlations.
There could be correlations, which sounds so on the picture, right? If you had a picture, there's a snow, all those travel times will be affected at the same time, right? Either nothing or everything will be affected, right? So there are correlations, right? What else? Complexity, okay, what else? What do you mean by complexity?
I mean, mean and standard deviation is probably not the complete characterization of the probability. If
you say they are Gaussians, it is, but if this is much more complicated, you need to have more parameters to fit, yes, and therefore you need more data to fit, right? So clearly if I say it's Gaussian, it's easy, right? Because you have just mu and sigma. But as I said, maybe it's different distribution, not Gaussians, they're correlated. If I have already Gaussians which are correlated, I need to estimate so much covariance, right? So what else?
So my issue is at the end you have many different routings, and how do you choose the one that
No, you can say I want to find one routing which works for every scenario which I sampled. So you can say this one. I can say I want to have one routing that works for the average scenario I can sample, right?
But is that the right optimization function?
That's also a question. Is it the right optimization question to optimize?
We use rules that have like, I don't know, 2% probability that they will be completely disastrous, and maybe you could use like a little worse rule that is this always reliable.
So there could be also different objective. With something, maybe the one can be, I want to have the route which is good on average. Yes, but maybe it's also not the best one, right? What is the different issue?
worst case approach?
You can also think about worst case approach, right? You can say I would like to have a few scenarios. I want to find the route which is best for the worst case. And actually, this can be sometimes an issue when you think about some legal requirements. You cannot force people to work 15 hours a day, right? Maybe therefore it can be the worst case. Okay, so there are a few issues here. Maybe estimating this mu sigmas, if you already say it's Gaussian, can be an issue, right? Actually, for VRP, when you have like 20 customers and you have only 5 scenarios, it's already hard to optimize. So therefore, we cannot really afford for the simplex like the Gurobi and Cplex to have many scenarios, actually. Usually 5 you can do for 20 customers. Because actually it's a very hard optimization problem, some explodes very quickly, right? So there's a different issue that usually even if you formulate this one, you need to solve this one only approximately because it's very hard to solve it to good accuracy. So there's so many issues, right? So basically what is our thought about, maybe can we use AI to make this one much better, right? Because AI can learn from data, as you told me before, or my daughter told me, just learn from data, you do something, right? So let's speak about this one. So I will use reinforcement learning. How many of you heard about this one in the past? Okay, so you are experts, which is good. I have just few slides which my son hates because I use his picture. So basically, if you know already, this one will be very easy. And just say that if you put your son to this like machine, ask him to cut the grass, he will see all these buttons. He has no clue what happens, right? So basically, RL basically is the idea, like humans are learning, I can also teach computers the same way, right? What will a child do if I ask him to cut the grass? How many of you have kids? I see Mary is laughing. I know what will happen. So what your son would do if you ask him for the first time to cut the grass?
Depends on his age.
Okay, so maybe not like my son, but he just press some buttons randomly and will destroy the machine, right? But hopefully after destroying some like machines for many times, he will get some punishment, right? And I used to be having a picture of spanking the child. They told me in the States it's not allowed. Then Googled in Pennsylvania was allowed, but I just changed to some punishments, okay? But after destroying many machines, he will cut the grass, he will get some nice reward, right? This is the idea how humans are learning, right? So basically for machines, it's the same stuff. You have some agent, which is the RL agent. He observes the state where he is now. He sees a few actions to choose. Then he will choose the action, and then he will get some new state and some reward, right? For example, I'm here, I choose action go forward, I'm in a new state. There was reward basically almost zero, right? Because I just wasted my energy. But if I maybe achieve, I will take the water, I will drink, maybe there's a nice reward for me, okay? And actually, they use this one already for, let's say, trying to play game of Go, chess. You can also use this one to play some games, let's say some Atari games and so on, okay? So basically the optimization problem is this one. I want to choose a set of actions which are going to minimize the future rewards which I'm getting from the system such that there's some kind of initial state and some transition, right? Transition actually can be random, but doesn't matter. But usually transition depends on my state, my action, and some maybe randomness, okay? This is the RL in a nutshell. Okay, so basically what is my goal is to find some policy. Policy tells you what action to choose for a given state, okay? So for machine learning, for RL, my goal is to find some policy, pi, which will observe my state S, and then we'll choose some actions, what should I do, okay? And usually basically what we do, we just create some deep neural network where thetas are the parameters of the neural network, okay? So get some few fully connected layers, doesn't matter, get some deep neural network. Theta are my weights. I want to modify the weights such that the output of the network will tell me what to do, which will maximize the reward, right? Okay, so basically sometimes what we assume is a stochastic policy where for a given state, I will get different probabilities for different actions, okay? It's called stochastic policy. I feed my state into the neural network. I will get some probabilities as output, right? They will sum up to 1. And for every action, I will have 1 probability. This one tells me just choose this action with 10%, 20% for this action, and so on, okay? And then I want to maximize my cumulative reward, which is now a function of theta, right? Because my actions, which I'm choosing, are a function of theta, okay? For a given state, initial S0, I will feed S0 to my neural network. I will get a bunch of probabilities. I will just choose some actions accordingly. We'll go to next state, and so on, okay? Now this one is function of theta, okay? Basically what can happen, maybe as I start using my policy, I can produce this trajectory, which is quite good, or maybe I'll produce this trajectory, which is quite bad, right? So basically what we can do, we can use policy gradient, which somehow optimize my theta such that I will increase chances for this to happen and decrease chances for this to happen, right? That's the whole idea, okay? So how many of you know policy gradient or some algorithms to train RL? So there are a few of you, of course. You know, but actually it's not so hard, but you just make some experiments, you use your policy to choose something, and afterwards you just compute some gradient of this function j of theta. And then you want to actually maximize, so therefore you take the gradient ascent step, okay? It doesn't matter much, but you can compute this j of theta, or the gradient of j of theta, just by evaluating the policy, and you multiply by the reward which you obtain, and this will optimize your neural network such that it will produce better and better trajectories, right? Cool. So, any questions so far? Okay, so let's now see how you can use this idea for TSP. Have you heard about TSP before, right? Traveling Salesman problem, basically you want to find a path which connects all these customers, all the nodes, by single path, right? You will not go to the same customer twice, just one path going to every single customer in the graph, okay? So basically, this was studied already in optimization for many, many years, also in graph theory, but also actually in deep learning, people said, hey, we can use this RL, reinforcement learning, to do many games, right? We can play the game of Go. I think there was a paper where they beat the champion. Can we also use deep learning to translate language? We can also use deep learning to describe images and so on. Why not to solve the TSP problem, right? And just the whole idea. Like, there was 3 papers which are very, very breakthrough. So I'm thinking about, I want to solve TSP using RL, okay? There are basically the thing that we discussed now. You do something, you see it's wrong, you try to do better, right? Like humans do. Okay, so basically, let's now think about how to translate the graph problem we want to solve, right? I get a bunch of nodes as input, and then I want to produce a route as output, right? This is a TSP, okay? Let's now start with the sequence-to-sequence models, okay? So let's say I'm a student, you put into some encoder, and then you go to French, right? Who can speak French? I can't, so it will be terrible French, but doesn't matter. But you can translate English to French, or English to Arabic, doesn't matter, right? So basically, question will be here. Can we map this TSP problem into sequence-to-sequence models? Maybe we can, right? And this was the paper which this one tried to do. This one said, okay, I will try to think about my set of customers, or set of nodes as a sequence of vertices as an input space, right? I will feed them into some encoder, which will be actually LSTM cell. I will just feed them one by one. Afterwards, I have some vector, some embedding of the whole problem, right? Using this one, now I will go to decoder to produce my TSP route. Okay, very simple idea. So basically, in this case, what I have a bunch of customers, which every one will be given by XY coordinates, right? I got in this case 5 customers. I will feed them into LSTM cell, right? Does everyone know what the LSTM cell is? Some people know. I think I have it here. So basically, LSTM cell is some neural network module where you have some hidden state and cell state, right? And basically, if you feed some input X, you try to update the hidden state and cell state, right? So basically, if you think about the language model which we had before, I can go a sentence, I is a word, I feed into the encoder, into LSTM cell. They can feed M, a student. I will basically feed all these 4 different tokens. And afterwards, the hidden state and cell state of LSTM cell just understand the input sequence, right? So we can feeding all these inputs into my LSTM cell. At the end, this agency should understand all the inputs, right? Also order of them, but they should understand the input, right? And afterwards, what I can do, once I feed all these customers into LSTM cell, I can just now say, hey, now I want to produce answer. I can go to different LSTM cell, but I will get some probabilities for the next nodes to visit, right? Almost like stochastic policy, I feed the state, I will get some probabilities for the next actions to choose, right? In reinforcement learning, basically, this is how you teach the RL. You try to run, you try with some state, you see some actions. In this case, you can see 5 actions. There are 5 different probabilities. I will just choose randomly, follow me the probability, and then afterwards, basically, what I will do, I will just move to this customer, right? So now, basically, what happened? I know the whole problem. I start producing the answer. I will get some action to choose maybe this customer. Then I choose him. I say, now I'm here. What to do next, right? I'm in the next state for the RL. Now he will tell me, okay, you have still only 4 options to choose from. I will maybe go there, and so on and so on, okay? So basically, this is a way how to encode a set of customers, set of nodes, into some actions I can choose, right? And my training basically will be choosing these parameters of these LSTM cells. This is my RL training, okay? Any question for this one? Do we understand this idea? I'm just feeding all the customers which I have. After I fed all of them, I just start producing the answer, right? Very simple. Who don't like this approach? Yes, please.
It's not an issue that the input sequence is not a sequence, it's a set, right?
That's my issue, right? It's
Well, I mean, that's
no.
better here because...
Okay. So question here. Once I train this, I have this vector here, right? That's actually what you want to say. If I permute the input, right? This is the same problem, right? If I permute the input, it's still a bunch of customers I need to visit, right? But for LSTM cell, this will be a very different vector, right? Different state of the cell and hidden state, right? Will be very different. So clearly, actually, this is wrong approach, right? But remember, this was in 2014 or 13, I believe. So there was no transformers yet, okay? But back in 2013, basically what happened, this was the paper which they had, and clearly it's wrong because it should be set to sequence, not sequence to sequence, right? Because clearly yes?
But then you have data attribution for P.
Yes, that's true. You can always permute and see, yes, it's there. But also it's headache because it should be set, not sequence to sequence, right? But this was really before the transformers and so on were invented, okay? But we understand the idea. I will just try to somehow decode the input and also define something which will give me the policy, right? Then some just sample probabilities, and then I use this policy gradient to optimize my neural network to maximize my reward, right? Please.
I have another issue with this because
I get much more issues than you.
the size of the problem is sort of can be big, right? And then I have a constant amount of memory for representation. Is that
Again, it's true. So basically, as someone said, if I want to scale this one to million of nodes, and you still have only like one or two vectors to represent the whole stuff, is issue, right? Completely, I agree with you. Therefore, actually, in the paper, I will go there a little bit afterwards. Some speak that they want to use some attention already. So there was 2013, 14. They already thought about some attention inside. To really don't really look for nodes which are far away, but somehow local to me, okay? But it's also an issue, because you want to now feed the whole sequence as, like it's a sequence, but it's not sequence, right? Cool. So we understand basically roughly what they did. I somehow feed the customers, I will get some probabilities as an action, as my stochastic policy. Then I want to sample some action, and then I will go to this customer, and now I go to next customer, and so on, until I finish the whole TSP route, okay? Cool. And in some sense, you don't have labels because you just compute the distance of this route, right? So this is actually your reward, right? It's really given because you're moving in a graph, right? Which is quite nice. Okay. The issue is also for us, because if you want to go to VRP, when you can have some demand for customers, right? Once you visit some customer, his demand will basically change, right? Maybe I want to have 5 items, car will come to my shop, and car has only 3 items, right? So then I will change my demand, it's now only 2 items left, right? If I use LSTM cell, I need to feed everything together to the LSTM, right? It's very, very hard when you want to do VRP, when basically maybe car has not enough capacity when you visit my customer, right? Okay, so there usually, for VRP, there could be static element, which basically is the coordinates in the map, with dynamic basic elements, what is my demand, right? Okay, so basically in this case, it's very hard to handle this architecture even when you have multiple demands which can change, okay? That's all what to remember about this one. Okay, so basically what they did is for the TSP, in the paper actually, I think they managed to publish this one in 2017. They also use some kind of attention. Basically, let's say once I'm somewhere in the graph, maybe here, which is my query, my location where I'm now, I just want to use almost like attention, right? I know where I'm now, basically I can think about the other customers where they are, and in some sense I want to compute some attention to tell me where to focus in the graph, right? Because clearly when I'm here, let's say in Bratislava, I will not really think about nodes in Košice, right? Because it's maybe far away. So the same idea was here to introduce this attention, to think about some small set of graphs or nodes to somehow consider when I'm moving to the next customer, okay? So this was the whole idea of attention in this huge problem, okay? And basically, there are some examples here. Basically, when I have policy, I get a bunch of probabilities, right? I can choose the one which is the most likely. This is called actually greedy. So once I choose the highest probability, I produce some route, which is called greedy. You can see here, if I use this, if I train this RL, on the left is the greedy selection, which somehow was having the cumulative route, let's say 5.934. Actually, this one is optimal. It's the shortest possible path, which you can see is much lower by, I think, 0.3. But also you can think about, maybe I don't want to choose the greedily to have the highest probability to choose from, but maybe what I can do, I can maybe just choose few of them, right? Or I can maybe just think about I get some initial design, I can maybe do some small optimization afterwards, right? And usually those ones will improve, right? But actually this is still good because if you choose greedily, it's quite decent, right? So you can see, yes, I can train RL to solve TSP problem, which is combinatorial problem, right? I can train it. It's roughly not perfect, but it's good enough, okay? Okay, any questions? And also you can compare this one with the optimal solution, but also you can compare with different heuristics which are out there. And some comparable, when you think about Christine Fiddles or other tools from Google, it's some comparable, right? Sometimes better, sometimes worse, but it's not so terrible, okay? And it's very simple RL to train on some random data which you can generate, and some works quite well, okay? Now let's go to VRP. Now basically I have multiple cars, I can have stochastic demand and so on, okay? So clearly if I think about VRP, I need to have the capacity of the car, right? Also need to have some demand of customers, right? Because basically there's a problem. I have a bunch of customers, I get some capacity of the car, I need to basically now play some game where I will try to randomly explore different options, different policies, and choose the best one, right? Which is minimize maybe distance, okay? So basically, if I go to some customer, let's say imagine I will have L, which is my capacity of the car. If I go to some customer and who has demand which is larger than my capacity of the car, then I just fulfill something for him, but there will still something left, right? For those customers which I don't visit, the demand will stay the same. And also after I go to some customer, my capacity basically will be decreased, right? Can go to 0 if the demand was much higher, or can be something positive if the demand was lower than my capacity which I was having in the car, okay? Does make sense, this one? Okay. We use now different architecture basically, which is transformer-based. You can see now I don't feed this LSTM cell because it's really set to sequence, right? So now what I'm doing, I'm just doing classical attention. I have bunch of input customers, right? Which basically can be the coordinates x, y, some demand. I try to embed this one into some vectors, and then I will do attention to give me some chances for the next customers to visit, right? It's actually classical attention algorithm or architecture to define, but still I will start producing sequence, right? Basically to embed input, I use attention, and now I start producing sequence as output. Almost the same as language, right? In language, you also have input, and you try to produce some sequence as output, right? Cool. So how it works? I'm showing you here box plots for some small VRP instances with 10 customers or 20. And in this case, we knew optimal solution because it's a very small instance, right? So basically what I'm showing here is basically a box plot showing you maybe like 1,000 different instances or hundreds, I forgot the number. So I'm showing you that what is the gap, optimality gap, right? Which means my cost minus the optimal over the optimal, right? So what you can see here, if I use greedy selection, which means I choose the action which is the most likely, I may be like 4% gap, optimality gap, right? If I something about, I will do beam search, do you know beam search? If I have a graph, basically I can try to keep the 10 most likely scenarios, right? If I start, I have many options to choose. I choose the 10 most likely one, right? Then we'll go to next point. I will evaluate all those options and I'll keep the 10 most likely, okay? Because I'll see if I go to beam search, is maybe on average, maybe 1% gap, right? Also, this beauty is that you can evaluate the policy very quickly. If you think of optimization or our tools or all those different heuristics, they take forever to evaluate. But RL is very fast to evaluate. You already learn the policy, right? And you can also see something else. If I go to 50 customers or 100, now we cannot find optimal solution because it's too large. So basically what someone did here to compare the fractions which are basically better using this one than the column. So this one tells you beam search on 85% instances is better than greedy selection, right? What is important to say is that this RL beam search is 60 times better than OR tools from Google. So basically on 60% instances, the RL was better than some OR tools or different heuristics you can think about. You can see the CW or SW and so on, some heuristics. And actually these are almost always better than those, okay? Cool. Any question about this? So this one tells you that using this RL is not so bad because you're almost always beating different heuristics you can use to solve the same problem. And the beauty basically is that if you have a new problem which is coming to you, you can just evaluate very quickly, let's say in a few milliseconds, where all those different heuristics will need to have time to optimize a given problem, right? Okay, actually this one is inference time. You can see that all these different tools are increasing computation time. This one increases the instance size, where the RL is basically just very tiny increase of time. Okay? Let's now see like one experiment. I will show some animation. Basically what we did here is I tried to think about where's the attention in a map, okay? So if the animation will work, basically I will show you here a YouTube video which we have. Okay, so now I'm trying to produce some route. And you can see here that I have still 14 items in the car. I ignore this point because I knew I need to do 3 routes. Actually, the RL knew I need to do more routes than going just there. Okay? So we'll just run it one more time. Hopefully, I will show one more time. Again, I start with maybe I have capacity of car 20. I go to this customer. Of course, my capacity will change. Think about now. I had still 14 items or 8 items in the car. I could go there, right? But the RL somehow already learn I need to go there maybe 3 more times or 3 more times. It's not just local heuristic which you learn. It's much more complicated, okay? And on the picture on the left, on the right, we somehow show you here, if there's some nodes somewhere on this white area, I would go there. So this is I'm trying to like mimic some kind of like arbitrary new node somewhere in the graph. So it shows you the likelihood to go to these nodes. It's really just almost like locally thinking where to go, okay? Cool, so this actually is one example of for different VRPs, 20 or 50. So it shows you what's the greedy selection, which is at the top, which basically only choose the one which is the most likely. And if you have this beam search, it can be much more smart, okay? But still somehow shows you that it works, it's not so bad, okay? Now, this was deterministic VRP, when we knew the demand for sure, also travel times for sure, right? And now think about the stochastic one. So basically the whole idea is that I will observe some features which can influence the travel times or demand. I will just build some RL model using this data. And then when I observe something new, I can just use the RL to produce the path, okay? Or the routes, okay? So we somehow simulated some kind of random variables. Basically in this case, the C will be some cost, which will be random. And also we put some extra cost here at the end, which is called actually, I think, recourse or something like that one. If I go to customer, which I don't have enough capacity, and to go to depot to refill. Okay, so this is actually what we want to optimize. Of course, could be changed to the worst case scenario, can be changed to some quantiles and so on. For simplicity, we just use just average scenario we want to optimize. We built some random data where every travel time or demand will be some function, some random function of some features. So in this case, this what I observe for some scenario is given some base value, some function of features plus some random noise, okay? So you really just want to build some random data. okay, which you can generate. And this accuracy is also the same, but now we also feed the external features as well to the input, okay? And we compare with 3 different heuristics. One is tabu search, one is ant colony, and one is this CW heuristic basically to solve this VRP. But clearly, all those algorithms are not designed for random features or random data. So basically, what we did, given the new features, we go to database, find maybe then k closest scenarios, and use them to optimize, okay? And actually, you can see here that if you use different like VRP instances, 10, 20, 50, 100 customers, you can see that this RL is actually much better than the others, okay? It's much better. It's basically the cost is actually much lower than all those different scenarios which you can think about. How much time do I have? 15 minutes or 10 minutes? Okay, okay. So basically this one tells you that it's actually much better than using those classical heuristics to optimize when you have stochastic travel times or stochastic demands, okay? Also for inference time, you can see here that as you increase, let's say, from 10 customers to 100, the cost of this one basically increased from 1 second to 123 seconds. Also for this one, basically increasing, but for RL, it's almost like evaluating the policy, which is almost nothing, okay? It's almost basically scaling linearly in time. Okay, so overall, we can improve by 2% or 3% when compared with different baselines, okay? Now, this is the end of the first part, and now my student told me, Martin, it's nice, but there's everywhere in news ChatGPT, right? Can I use ChatGPT to solve it for me? What do you think? Can I use LLMs to solve it? What do you think? I just go to ChatGPT and say, hey, I got some customers on these locations, I got some demands, I got some depot in location 5050, just solve it, right? Can you find me the shortest path? How many of you know of LLMs, like ChatGPT, transformers, llamas, and so on? Okay, so what do you think? Can I solve this problem using LLMs?
By generating code.
Okay, by generating code, okay, yes. Okay, so maybe you can write me some code to optimize some heuristic, right? Implement some heuristic, okay? But can I just do it just asking question and hoping he will give me the answer straight away? What do you think? Because I know people are using ChatGPT every single day, right? So is it good enough to solve these problems? What do you think? Should we vote? Get some chocolate for that if you win. So who thinks it's, I can ask this question, he will give me the correct answer? Okay, so you won, because it's very bad, actually. And the reason is that even to compute the shortest path, actually, there are some papers showing you that you can use transformer to find the shortest path, but number of server attentions are needed the same as number of nodes. So if you say I got 8 server attention layers, in one prompt they can find shortest path up to maybe 8 nodes maximum, right? So clearly, if you just take some ChatGPT pre-trained model, there's some capacity what you can do, right? So therefore, we thought maybe what we can do, we can create some kind of like prompting strategy to decompose the problem into small subparts and then solve the subparts and then combine into one answer, right? So actually, this is a paper from, I think, this year's NeurIPS, I believe. We someone tried to propose this strategy to somehow say, hey, LLM, you have this problem, suggest some ideas how to solve it. Maybe you can suggest few algorithms or few decompositions. Then you can perform each subproblem you can solve using ChatGPT, and then you can combine. Okay, example here. You can ask him, hey, what are the heuristics I can use to solve this problem? He can give you all these heuristics, right? All of them. You can say, hey, I just want to choose one by one. I can maybe use the nearest neighbor algorithm. If you heard this heuristic, basically just choose the customer which is closest to you, go to him, and then continue like this, right? We can ask now, okay, let's try to use this nearest neighbors algorithm. Now, what are the steps? It tells you, okay, start with depot. Now, compute distances to each of them, right? So this is basically one LLM call. I'm here, compute distances to each single customer, right? Then choose the one which is closest. Now move there, right? So decompose this problem as a step of algorithms which you can run in LLM, okay? Now basically you can say, okay, I'll go to customer, then you compute distances, different LLM call, compute distances, and then you just choose the closest one. Now we'll go to customer number 3, and you can also get, okay, I will go to customer number 3, again, compute the same algorithm, find distances to different customers, and you can choose the closest one, and repeat until you produce this route, okay? And actually, you can use the same strategy for every single heuristic you can think about or LM can think about. And then you can also think, hey, I got this route, can you improve this one? And usually in optimization, there are these strategies to try to switch some customers, right, in the order. Which is called 2-opt or 3-opt. I will just change tuples or triples and see if these are improved or not, okay? So basically, in this case, what you can try to guide him to produce the actually correct answer, which is like customer 1, 3, 2, and 4, okay? So yes, you can use LLM to solve even these problems, but it's actually much more expensive, right? So we thought, hey, I just want to skip this one because it's showing you improvements, doesn't matter. I want to go to this one, some reasoning task. Imagine you can ask this problem. Bat bakes 2,000 batches of cookies in a week. If cookies are shared among 16 students, equally, how many cookies does each person consume, right? Clearly, it's a problem which you can think about to ask LLM, right? And most likely, actually, LLM will fail, okay? But if you use the same strategy to say, hey, you have this problem, try to decompose into some sub-problems, try to combine them as an answer, it turns out the same strategy which we thought about LLMs for VRP actually also works for reasoning problems, right? I'll show you that there are different problems here. This was like the reasoning for math. Usually, there could be some kind of like thinking about. I can ask question, did Aristotle use a laptop, right? You can ask this to LLM. To answer correctly, you need to think about when laptop basically was invented, when Aristotle basically lived, and then you combine this one to say, no, he couldn't, right? And those things can be like this one, which is very simple. Like you can take some, maybe take the letters, last letters from the word Clinton, blah, blah, which would be N-A-A-Y, right? So we sometimes try to see, can we use the same strategy for this reasoning task, math tasks, and so on? And we sometimes try to compare with different prompting strategies. Actually, this one is the input out to just ask, okay? We just ask, 67% is success rate. You think about this strategy which can somehow improve your reasoning. Actually, it was improved to 74.6. And actually, those are some chain of thought which should also think or work similarly, but they are not as successful as this one, okay? Just think about this one. That you can also think about arithmetic problem, common sense, symbolic, and so on. So this strategy with this prompting should improve for all of them, okay? Just if you are in LLM, you can also check afterwards. And there are different problems here. I just want to waste time because we don't have time. But you can ask different questions, you know, just more examples.
I'm sorry to jump in. This is
yes.
without any tooling or anything like that, right?
There's no tooling. Now basically just ask question, he will decompose himself, he will guide himself to the correct answer. We call it self-guided exploration. Any questions? Yeah, please.
In what sense is this different than all these reasoning models that end up being all the rage?
Now which one, the R1 from DeepSeek or?
Yeah, or the QEQ1. As in, like, in what sense is sort of self-guiding reasoning different,
yes.
Like self-guided exploration
yes.
different from, wait, I have this sort of, which is what.
Okay, so I know only a few of them, but say one of them is the chain of thoughts, right? You know,
it's
one,
extended chain of thoughts.
Yeah. So I don't know the one which you mentioned, we can check afterwards, but say we study like chain of thoughts where you just tell him, just think about every single step, right? And usually this one improves by, let's say, 2%, 3%, like I was showing here for a few problems, actually. There was some small improvement, of course, because he will try to explore and think. Let's say, this one is, so this one is a chain of thoughts, right? Sometimes it actually gets worse, sometimes it will get better. And I think, so in this case, it's TSP, so in this case, smaller is better, okay? You can see, if you don't do anything like that, you have, let's say, 8 nodes of customers, go from 46 to 39, so it helps you. But actually, we go to 8. Because somehow chain of thought is just a little bit still trivial.
Right, no.
You think about this one, so clearly it's not sufficient enough to help the reasoning to be much better. And I think this is also we have the same for logical problems. You can see here, again, chain of thoughts can help you maybe by 2%, but this can actually help you by 7%, right? So it's basically a different strategy to guide him to be better in reasoning. It's not a final answer, actually, so there's still research to be happen here. Okay, so that's it. Thank you.